Okay, it's done. So in last class we have already started the non-busy waiting solutions, and we saw one of the problems named producer consumer problems. And producer consumer problems, we used a ordinary variable called count variables. And if we use this kind of ordinary variables, then we figured out that in some cases both process may enter into the sleep mode. Both process may enter into the sleep modes. To avoid the situation, um, also to implement a non-busy waiting solution, we use the semaphore variables. In our last class, we talked about the binary semaphores. Yeah, I showed you the how you can implement the binary semaphore and its algorithms, but we didn't check this some properties for some properties like no only three properties, but mutual exclusions, bounded waiting, and another is sorry, first one is mutual exclusion, second one is progress, and third one is the bounded waiting. We have to uh, check these properties for binary semaphores variable. Okay. Uh, all right, let me share my screen. Okay, it is, I think I shared the screen. Okay, let me turn off my video, then it will be smooth. Okay, now let's check. Let's see again this binary semaphores and its codes. You know the binary semaphores. Semaphores is nothing but it is a structure type variables, and it contains two fields. If it is a semaphore, it contains two fields. One is called value field, another is list field. List field. List field. List is nothing but a queue. Okay, queue field. Nothing but a queue. List is queue, and it is binary semaphore. So value field is either 0 and 1. So how you can implement this type of semaphores? Semaphores is kind of there is apply. You can use this two function. One is called wait function, and inside this after this wait function, it has parameters is semaphore parameters, and then this is the critical section, and another is the signal function. Also, its parameter argument is critical section. These are the two. If you have the P1, P2, P3, several process, you can say each process has this critical section. This process also has critical section. This process has also this critical section. So this two function is you need to for entry add all of this process for entry as well as the exit section. Okay, these two function you can add for both of these for entry section as well as the critical as well as the exit section. So entry section is implemented by this wait method call, and exit function is implemented by using signal method calls. So let's see that how what is inside for this wait as well as the signal function. I already showed you this before. It is wait, and then its one parameter is semaphore parameter. Semaphore. Because today we'll implement their three properties of synchronization mechanism. We'll check these three properties. If you say this s dot value, if s dot value is equal 1, means that there is no process inside this critical section. Inside a critical section is free. Then you it will make this s dot value is equal to 0, means that this process is now enter this critical section, and then else what it will do if it is not 1. If it is not 1, means that one process is already inside the critical section. If it is not 1, s dot value is not equal 1, means that already one process inside this critical section. So another process will put into the queue, or and then it will be then in sleep mode. Put the process PCB or process control block in in s.l means that this field, this two field for semaphore. One is value field, another is the list field. List is nothing but a queue field, and then you need to sleep this process. Sleep this process. This is the wait function. This is the wait function, and for the signal function also take the semaphore as a parameters in here. Semaphore parameters s, let's say s, and then what is the function inside in here? If it will check this queue list, if s dot l is empty, this is the exit level code is empty. If it is empty, then there is no process for waiting inside the queue for entering the critical section. So then it will make this s dot value equal 1, means that no process is interested for entering the critical section. So it will turn this value field is 1, so that the new process can enter this critical section. If the list is not empty, means that some process is already interested for entering the critical section, but they are in sleep mode. So if it is list is not empty, then you need to select a process from this list for wake up. Select a process from s.l. Sorry, my turn on my pen. Okay, select a process from s.l, and then you make two these things wake up, and you go for this wake up call. Okay, this is the code for signal, and this is the code for this wait. And between this you have this critical section. Between these two here, this critical section, this is entry level, this is the entry level code, or this one is the exit level code. Okay, exit level code. Now let's check this type of things is actually perform the mutual exclusion or not. It fulfill the, or it granted the mutual exclusion. Mutual exclusion or not. Let's think about this. Here is one process. First, let's say this process P1 is trying to enter in the critical section. At the beginning, what is the value for this process? Value field for semaphore. At the beginning, semaphore value is always 1. Means that critical section is empty. So process P1 will be enter this critical section. What it will do? It will make this s.bell is equal 1. Then it will make this s.bell equal 0. So it will be make it s.bell equal 0. And process P1 is entering that is currently enter is currently inside this critical section. Next, let's say process P1 is trying to enter in the critical section. Then what it will do? Again, it will call this wait function at first. Wait function, and in wait function, what it will see? It will see from here. It will see that s.value is 0. It is not 1. So it is 0. So it will execute this else statement. What is else statement does? It will put this process inside this list. Means that your semaphore, there is two field. I already mentioned. One is the value field, another is the list field. There is two field. List is nothing but this is the list field. This is the value field. Value is currently 0. This is 0, and the list is empty. So what it will do? It will put this whatever this function P1 will be in here in this list. And next, let's say this process P2. Again, P2 is trying to enter in the critical section. It will see this value field is 0. So it will be inside this list. So P1, and then it is queue list. So P1, and then it will be, and next value will be the P2. First P1 and then P2 will be here. Will be the list value. Now let's see this process P1 is from here. You can see that at a given time only one process can enter this critical section. So it satisfies the mutual exclusion. Semaphore is satisfy this mutual exclusion. Now let's see the what is the progress. Progress is nothing but this: if one process inside this critical section, or if no process inside this critical section, then another it shouldn't block this another process for entering the critical section. So let's check this. Let's take this process P1 is already inside this critical section. Process P1 is already inside this critical section, and process P1 completes its execution. Now what it will do here is to process. Then in wake up signal in here it will check this if s.bell is empty or not. But s.bell is not empty. Now let's check this. What it will do? It will see not empty. So it will select a process. It will select this process P1. It will select this process P1, and it will be wake up, and then it will be enter this critical section. The process P1 will be enter this critical section. This is queue. This is queue list. So process P1 enters this list value first. So process P1 um, will be delete from this P value from this list first, and then P2 will be take from this list. Okay. Now let's check this. Now P1 is entering this critical section. Here let's see again. P1 completes execution, and then it will check this process another process, let's say process P2. It will check this queue is empty or not, but queue is not empty. So then it will wake up this process P2, and P2 will be enter the critical section. P2 will be enter this critical section. Now here you can see that whenever the process enter this critical section, is completely depends on this wait the process which is called this wait function first. Wait function first. It doesn't rely on this another process executing for this another process. Whatever it execute this non-critical or critical section, it's never mm, for entering this critical section, it's completely depends on this wait the process that calls this wait function first, and this function will enter this critical section first. It doesn't depends on this other process. It's whether it's execute the non-critical section or not. Okay, so here progress is always satisfied. Progress is always satisfied. And next, let's see that another is bounded waiting. Bounded waiting satisfied or not? Okay. Bounded waiting. What is the bounded waiting? Bounded waiting means that process, let's say process P1 at first enter this critical section, then process P2 also shows for entering this critical section, and process P1 completes this critical section, and again process P1 can enter this critical section or not by waiting the process P2. By waiting process P2. Again process P1, if process P1 can enter this critical section again and again, then that means that bounded condition is not guaranteed. But if the process P1 completes its execution in critical section, and then also by this time process P2 also shows interest for entering the critical section, and if the process P1 cannot again, if process P1 cannot again see critical section again by waiting this process P2, means that you guarantee the bounded condition. Now let's check this bounded condition in here guaranteed or not. Let's see the process P1 at first trying to enter in the critical section. What it will do? Process P1 is enter the critical section, and let's say this first is semaphore value is always 1. At the initial value, semaphore value is always 1. Now what it will do? Process P1 call this in this function, wait function, and what here it will find this as value is 1. So it will make this as value is 0, and process P1 will be enter the critical section. Process P1 will be enter this critical section. Now process P1 is entering inside this critical section, and by this time process P2 shows the interest for entering the critical section, and it will call this again. It will call this at first. It will call this signal wait function first. Wait function. Sorry, this is critical section is that one. Let me. Yeah, this is the critical section. Let me copy this signal function. Here is the critical section. Process P1 is entering the critical section. Now, process P2 shows interest for entering this critical section. What's it will find in here? It will find this as value is 0, currently 0. Then it will execute this else code and puts the process uh, in list value. So process P2 will be waiting inside this queue list. Process P2 will be inside this queue list, and it will be in sleep mode. Next, let's say process P1 completes its execution, and it will call this signal function. What it will do, it will call this signal function. In here, it will see that it will see what it will find. It will find this s dot l is empty or not, but s dot l is not empty. Currently, P2 is waiting inside this list value. So so it will execute in here else statement. It will select the what it will select. It will select a value from this process from this list. This is nothing but P2, and it will wake up. So process P2 will be wake up, and let's say process P2 will be wake up, and next step is the critical section. Process P2 will be entering the critical section. Now let's see this. If process P2 is not is already inside the sorry, let's check again. Again, this process P2 is now wake up and for entering this critical section. So let's see from here you can see that there is no chance this process P1 makes waiting for this process P2, and process P1 can enter this critical section again and again by waiting this process P2, because you see in here every process when it is called, let's say again P3 is, let's say another process also, there is two processes waiting, and by this time process P1 again call in here. So what it will find? It will find this as this value is 0, as value is this value is 0. So what it will find in here? It will be uh, inside this list. It will be in here P1. So there is no chance the one process will enter complete the critical section again and again after a process actually shows the interest for entering the critical section. So here, of course, bounded condition is bounded waiting is guaranteed. So in binary semaphore, you can get the mutual exclusion, as well as you can guarantee the progress, and you can guarantee the bounded waiting. So it is one of the best method, and this is the best method actually, not one of this is the best method. Nowadays, all modern computers, modern operating system use the binary semaphore techniques. Okay. Also another some properties is that it is multi-process. It is not a two-process solution. Okay, it is multi-process solution. You already know about this two-process solution, like turn variable, also interested variables, and another is Peterson methods. These are the busy waiting solution. These are busy waiting solution, but these are only apply. You can apply only for this two process. But for binary semaphore, it is also the multi-processing system like log variables and TSL method. Also, it executes in kernel mode. It executes because signal wait this function, wait function and signal function. These are two system method. So it should executes in the kernel mode. Also, these are the hardware independent. Even though there is two system called in here, signal as well as the wait, this the two methods. These are two system method, but this two method is common for all operating system. So it is hardware independent. Also, you know that TSL method is hardware dependent. This is a special command. It may not support all of the computers. Okay, but wait and also the signal is available for all of operating system. It can support every machines. So we can say this is hardware independent. And some other properties is, we already know about that. It satisfies this mutual exclusion. Also, progress is satisfied because the decision doesn't postpone here independently, because here which process will be enter the critical section. It's totally depends on this, which calls the uh, wait function first. Wait function first. It doesn't depends on this another process is executing the non-critical section or not. It doesn't depends on this another other process. So your progress is satisfied. Also, bounded waiting is also guaranteed. One process cannot enter this critical section again and again by waiting the other process. Actually, which process shows already shows interest for entering the critical section. All right, this is the binary semaphore approach. So this is a best approach. Now we'll learn some another approach is called counting semaphore. Okay, these are the second approach to do learn this counting semaphore. It is almost same as this binary semaphore, but you know that in in semaphore is structure variable. It has a value field as well as one. It has a value field as well as another is list field. In binary semaphore value is 0 or 1. This is that is the reason it is binary. But in counting semaphore, its value, there is kind of initial value. So before we start this value field, what is the value? Let's actually examine some properties of counting semaphore. This structure is similar as the binary semaphore. This is true. Instead of Boolean variable, here value is a integer value. Let's say this value, what is this value? Integer value reference. If this value s dot val you set as the 3, what does it means? It means that at a given time, 3 process can enter the critical section. Okay, the process can enter this critical section. This value field actually refers that point. What about this? If value is 2 means this at a given time 2 process can enter this critical section. If it is 4, at a given time 4 process can enter the critical section. This is the value field reference. So here you can say that, okay, if 2 or 3 process can enter the more than 1 process can enter this critical section, does it guarantee the mutual exclusion or not? Actually, it depends. If some requirements, you know, this binary semaphore is implemented for all of these operating systems nowadays. Binary semaphore allows only one process for critical section, but in some instance, if you need to enter more than one process, if your requirement is that you allow more than one process inside this critical section, that time you can use this kind of semaphore approach, counting semaphore approach. All right. And let's say in some, if your computer is connected to total 3 printers. So if printer is a resource, if printer is a shared resource, here is total 3 process can use the 3 different printers. So you can enter this total 3 process at a given time inside a critical section. So in some instance, you may need to implements more than one process for entering this critical section. In that case, you will apply the counting semaphore approach. Okay, otherwise it doesn't. You apply some others called the binary semaphore approach. But one thing you need to ensure that this s dot val, whatever this s dot value you set, it is 3. So at a given time, maximum 3 process can enter this critical section. If it is 4 cannot allowed. Okay, 4 cannot allowed. This is the maximum number. This is a maximum number. You need to ensure by using this counting semaphore problems. So whatever this value for this value field you assign, the maximum number of that process can enter the critical section. Maximum if it is 3, so maximum 3 process can enter the critical section at a given time. Now let's see that how you can implement the semaphore variables. How we can implement the semaphore variables. Also, you know that in semaphore variables, you already know this wait and signal function and wait and signal, and you can also know this is also represented as one is P and I think this is B. Let me check again, double check again. I think this is P and B you can represent by using, give a minute. Yeah, first one is P. Also you can say you can also represent this, that one is up function, as well as that one is the down function. Okay, please keep in mind, but all are same function. Okay, same function. In some books or some instance or some operating system may use for this wait function, some may say it is P function, and some may it is a up function. And signal also represented as V as well as the down function. Okay, but all are same. Now let's see that how we can implement the counting semaphore approach. So we're talking about the counting semaphore. Counting semaphore. Okay, counting semaphore method. Here is also two. It's same approach. It is, let's say this is if it is critical section. If it is critical section, let's say this is the down function. Down is equivalence to the equivalence to your wait function. Down is equivalence to the wait function, and that is, let's say, okay, no, not down, sorry, up function. Okay. Oh yes, down. Yes, down is equivalence to the wait method or wait function. This is down. Let's say down semaphore, and also the up. Up is also takes argument as a semaphore. Now let's see that how we can implement this down and up function. Okay, here is down. Also, it has a parameter as a semaphore parameters, semaphore value. And what it will do down function? Down function, it will at first it will decrease the value for semaphore, decrease the value of semaphore, and then it will check if s dot val is less than 0. When it is less than 0 means that there is no slot for entering the critical section. Put then process PCB, put process PCB s dot l in list. Okay, queue list. Next it will be, and then this process will be sleep mode. And next what another thing is that up entry level is down and exit level is up function. That what is the code for this up function? Up also take this semaphore parameters, and then how it's work, it will increment the semaphore value as dot val whenever, and then it will be as dot val plus 1. It will increase this value, means that one process already completes its execution. Next it will check this, if s dot val is less or equal 0, means that one process is inside the queue list. We'll check again. Select a process from s dot l, and then you call this wake up function. wake up function for waking the process. And between this, this is the critical section in here. From here, you can see this is the down and this is the up. And between this, you have the critical section. Okay. Now let's check this how it works. At first, let's see this. You have semaphore, and you just assign this value field as a, let's say 3. You have 3, and then one list in here, and list field. This is the whole semaphore. It is the structure. It takes it has two parameters. Two parameters. One is the bell, another. Sorry, it has two field structure. It has two field. One is the value field as well as one is the list field. You set this for counting semaphore. You set this value as a 3, means that you allow maximum 3 process for entering the critical section. Maximum 3 process for entering the critical section. Let's check it. Let's say you have total 4 processes currently. Now, at first process P1, let's say trying to complete its execution, and it shows interest for entering this critical section. Then what it will do? It will at first call this down function. What it will do? It will see the semaphore value, and semaphore value equal value minus 1. Then it will make this value from 3 to 2, and then it will check this value is less than 0. No, it is not less than 0. It is currently 2. So then what it will do, and then it will enter the critical section. This is down function is done. This is down function is done, and next step is critical section. This is a critical section. So P1 will be enter the critical section, and next let's see this process P2. Call this down function again. And then what is down function will do? It will make this as dot bell equal minus bell equal bell. It will decrement one. Then it will decrement, make it 1 to 1, and then it will check this value is less than 0. No, it is not less than 0. Then it will be also process P2 will be enter this critical section. And let's say process P3 enter this critical section or not. Process P3 also, as usual, it called this down function. Down function, it will make this as bell equal minus 1. So it will be 0. It will be 0 now. And then it will check it is less than 0 or not. No, it is not less than 0. It is already 0, not less than 0, not a negative value. So process P3 also will enter the critical section. Next, let's say process P4 trying to enter this critical section. Then it will call this wait down function, and then it will, what is the down function here? It will make decrement this value. It will be 0 to, it will be the 1 minus 1. Okay, 0 or 0 minus 1 equal minus 1. Then what it will do? It will check this value. It is less than 0. So now this process P4 will be enter the list. Okay, and it will be the sleep mode. Okay, it will be block start or sleep mode. P4 will be entering the list or block state. Now let's see this maximum 3, whatever this value you set in here 3. So total 3 process you can enter the critical section. And then again, let's say this process P1 completes execution. Then it will call this up function. It will call this up function in here. What will up function will do? Up function will increase the value as 1. So it will be minus 1 to 0. Minus 1 to 0. Minus 1 plus 1 equal 0. So, and then if bell equal, you see here you check this condition where it is minus, less than or equal, why it is only less equal. You already see why it is less equal, because whenever you one function call this down, it will at first decrease the as value, semaphore value. So whenever it's negative means that there is no slot. When it is 0 means that already equal 0 means that there is a one spot a process can enter this critical section, because whenever you call this function at first you reduce the value of semaphore by 1. Okay, so that's why here is less than 0, but here is less or equal 0. Here you can see that 3 processes enter this critical section, and once P1 completes execution, it will make this minus 1 to 0. Semaphore value is 0. So that's why it is less or equal 0, means that if it is 0, if here it's 0 means that one process already inside this list or queue list. Okay, then what it will do, if it is less than or equal 0, condition is true, then it will select this process from SL and wake up. P4 will be wake up, and then next step will be the critical section. So P4 will be enter the critical section. Okay. Once this P2 also done, P2 will be called this wake up function. What it will do? It will increase this value as a 0 to 1, and then here 0 to 1, and then here it will check this condition less or equal 0. No, it is not less or equal 0. It is 1, already 1. So means that there is no process in the queue list. If there is one process, is P4 is already entered the critical section. So when it is 1 means that there is no process inside the critical section currently right now. No process inside this list currently right now. So now how many process here? P2 is completes. Now P3 and P4 inside this critical section. From here you can see again if process P1 is trying to enter this critical section, what it will do? It will make this s.s value minus 1. So it will be again 0. And process P1, if it is less than 0, no, it is not less than 0. So process P1 will be the enter this critical section. So now process P2, P3, P4 and P1 is currently under this critical section. Let's say this process P2 is again enter this critical section or not. Now total 3 process inside this critical section. Now let's say process P2 shows interest for entering this critical section. It will call this down function. So it will make this s dot value minus 1. So it will be the minus 1. So s dot value equal less than 0 means condition is true. Then this put this process in sleep mode. So it will be the P1, P2 will be inside this list, and it will be the sleep mode. From here you can see that at least here is s value is 3. So at best 3 process can enter this critical section at a time. Okay. So this is how we can implement the counting semaphore. There is a difference is that here if some instance you may need to more than one process for entering this critical section, this time you can implement the counting semaphore. Binary semaphore. By using the binary semaphore, you can use binary semaphore can allow only one process for entering the critical section. But one thing you need to ensure that counting semaphore, if it is as bell equal 3, you should ensure that total maximum 3 process can enter this critical section. It shouldn't be 4. Okay, it should always be less or equal 3. The maximum 3 process can enter this critical section. Other this list part is same as the previous previous binary semaphore. Okay. Also binary semaphore, also I already mentioned that binary semaphore is also the mutex. It is from the mutual exclusion. Binary semaphore is also mute, M-U-T-E-X, exclusion. Okay, binary semaphore is also known as the mutex because it's always guarantee the mutual exclusion. All right, this is the all about for the counting semaphore. Here, something you need to know about this counting. When I already explain everything in here. When semaphore value is positive, there is a space inside the critical section. When this value is positive, when the semaphore value is positive, when it is less than 0 or 0 to any positive value, means that there is one spot for entering this critical section. When this value is negative, when it becomes this -1, means that there is no spot for entering this critical section. So when a process call this down function and makes this s dot val is -1, means that this process should wait inside the list. Inside this list. So when it is negative value, means that there is no spot for entering the critical section. If semaphore value is positive, then a process can enter this critical section. On the other hand, if semaphore value is negative or 0, then process will be added to the queue list. Okay, even though it is 0, if it is 0, sorry, I explained it. If it is zero, also when it is zero, then also there is no spots. Okay. If it sorry, if it is zero, then it is fine. If it is zero, then it is fine. There is one spot. If it is less than zero, when it is negative, then there is no spots. When it is negative, there is no spot for entering. Yeah, only the negative cases there is no spots for entering the critical section. Okay. All right. These are all for this counting semaphore as well as the binary semaphore. This actually conclude the all about the mm, all about the process synchronization mechanism. At first, we learn the busy waiting solution, and then we learn the non-busy waiting solution. So these are the binary semaphores and counting semaphores. All are the non-busy waiting solution. You know that when a function uh, trying to enter the critical section, it moves to the sleep mode. Sleep mode. So when it is sleep mode, let's say you have four process. You have total four process in here. Process P1, P2, P3, and P4. Okay. When it is let's say process P1, if it is in case of binary process P1 is currently under this critical section, so then process P2, P3, P4 trying to enter this critical section, then it will be the block state. It will be the block state, means that your operating system, it is block state. Your operating system never schedule this process. Okay. In case of a busy waiting solution, what's it? All processes are ready state. So operating system schedule any process and it will execute unnecessary while loop. But here, whenever a process interest for entering the critical section, it calls the if there is no spot for entering the critical section, it calls the sleep method, and it enters the block state. And then wake up method actually awaken one of the process from this block state. Okay, so it is done by sleep as well as the wake method call. So here this is the non-busy waiting solution. All are the non-busy waiting solution. This keep in mind. So this all about the synchronization mechanism. We learn both busy waiting as well as the non-busy waiting solutions. Now let's check some items from some. Let's talk about some deadlocks concept from these deadlocks. You already know about these deadlocks. When two process is trying to two or more process is unable to proceed because one process is waiting for the another process. You already know process P1 is waiting for this process P2 complete execution, and process P2 also waiting for this process P1 for complete its execution. So this is the circular waiting. So no process can complete its execution. These are the deadlocks. Okay, before we start these deadlocks, let's check some what is the resources. Okay, what is resource? First, we will see about the resources. Again, we will check some what does mean by the resource. Okay, in computer resource, any physical and virtual components. Actually, first now we talk about the resources. Okay. So any physical and virtual component, both physical and virtual components is referred as the physical and virtual components. Components refer as the resource. Okay, refer as resource in physical and virtual components. Physical components is nothing but printer is a resource, or if you go for the CPU is a resource, and your computer's RAM is a resource. Okay, everything is resource. In virtual semaphore variables, you cannot see this variable, but this is a resource. This is also virtual resource. All right, but you have always you have this limitation of resource. Okay, you have limitation of resource, but you need to use it properly. And also deadlock is I already mentioned, two or more process are unable to proceed because this process is one of the process is waiting to another other process. Okay, now let's see that how actually a resource. Um, now let's check this. What is the necessary condition for a deadlock happen? There is what is necessary condition, necessary conditions for deadlock, deadlocks. Okay. There are four necessary conditions for deadlock. If one of them, if you one of them cannot happen, then actually deadlock cannot be happened. Okay. If one of them is missing, then deadlock cannot be happen. There is four things is needed for to happen to occur a deadlock. Okay, there is four things. One is for mutual exclusion. Exclusion. If there are some points, if needs this mutual exclusion, then deadlock. And then another is for hold and wait. Of course, hold and wait. There should be hold and wait. And see, there should be another thing is this no preemption of resource. I'll explain it one by one. No preemption of resources. Resources, and fourth one is circular weight. Circular weight. Wait, these are the four things for a deadlocks, for occurring a deadlocks. If you avoid one of these things, means that there is no possibility for the deadlocks. Okay, let's say you have two process P1 and process P2, and each process needs two resources. Let's say resource resource, and resource one of this resource, let's say numbering for R1 and R2. So if process P1, let's say process P1 already occupied this R1 resource, and process P2 is already occupied this R2 resource. Now process P1 is trying to, it needs two resources. So R1 is occupied and R2 is its request. So it's trying to enter, trying to access these resources. Then what's happened? This will be the in sleep mode. You see, these resources are already held by process P2, and similarly, process P2 is trying to enter this resource, trying to access this resource. Then it will be inside the sleep mode, because now this is circular waiting of this circular waiting for this process. Okay, if there is no mutual exclusion, if there is no mutual exclusion, means that two process can access the same resources. Let's say process P2 can access P2 can access R1 R2, and also P1 can access this R1 and R2 as well at the same time. At the same times, then there will be the no deadlock. But if you go for this mutual exclusion, there will be the inconsistency. The mutual exclusion, you need to maintain that things. Okay. So if there is no mutual exclusion, there will be the no deadlock. No mutual exclusion means that there is no restriction for accessing the resource. And hold and wait. Hold and wait means that process P1 already hold this resource R1, and it is wait for this another resources. That's why there is a deadlock. If process P1 is already hold a one resource R1, but if process P1 is not access get this another resource is R2, if this also if the process P2 release its resources, there will be the no deadlock. But process P1 hold and then wait. Let's say process P1 already hold this resource, the R1, and there is no chance to get this resource, this R2. In that case, if process P1 release this resource, then process P2 can take this resource and complete the execution. But here it doesn't. But in case of this process, once this process hold a resource, it doesn't release it. That's why there is a hold and wait situation will be there for occurring a deadlock. Okay. Another thing is this no preemption of resources. What is the preemption of resources means? Let's say this process P1 and P2. P2's priority is higher than, let's say, process P1. P2's higher priority is higher than this process P1. Let's say SJF algorithms, it has the less burst time or execution time, process P2, and then this process P1. So process P2 and its priority, let's say this is a higher priority. If higher priority process comes for executing the comes actually takes the CPU and trying to complete its execution. If higher priority process can preempt the resource from this lower priority process, that's R1, can preempt this lower priority process for R1, then there will be the no deadlock. But in that case, in operating system, you cannot do this. You cannot, once this process P1 hold a resource, even though it is lower priority, you cannot make it. You cannot preempt this resource forcefully. You cannot preempt this resource forcefully. You can preempt this process, but this resource you cannot preempt. That's why there is no resource. If there is preemption, if P2 is higher priority, P2 execution, and it can preemption this from the resource from P1, then it gets these two resources and completes execution. But it doesn't happen. So there is no preemption of resources. This is the one of the requirement for occurring a deadlock. Another is circular wait. Circular wait is nothing but this process. Let's say process P1 is trying to waiting for this process P2, and P2 is waiting for this process P3, and also P3 is waiting for this process P1 to complete execution. Now, let's say this is circular waiting. Okay, this circular waiting. If you make one circular here off, there is off. Here you can see this process P2. This process P2 is now doesn't wait for this another process. So P2 completes execution by taking resources. It doesn't need to wait for this another process. So it's completes execution, and then once it completes execution, then it's release all of these resources. Then process P2 completes execution. P1 completes execution by using the resources from P2 and some other resources. And once P1 and P2 done, then P3 also completes execution by taking the release resource from P1 and P2. You know that once a process complete its execution, it's release all of these resources. Okay, so from here you can see that if you break one circle, then there is a no deadlock. There is no deadlock. If you delete this circle, then process P2 completes execution, it will release, then process P1 completes execution, then process P3 will be completes execution. But to occur deadlocks, there is another necessary condition for circular wait. Okay, if you make one of these properties is invalid, then there will be the no deadlock. Okay. Now let's see that some topic on resources. Okay, let's check some resource. What is the type of some resource types? There are two types of resource. We can say there is two types of resources. One is single instance resource. Single instance resource. Another is called the multiple instance resource. Multiple instance resources. Okay. What is the single instance resource? Single instance resource, if you go for this multi-programmable computer, there is only one CPU. So this is single instance resource. CPU is a single instance. If you go for multi-processing, there is more than one CPU. This is called the multi-instance resources. If your computer is connected to only one printer, then it is single instance resource. If it is connected to the more than one printer, then it is multi-instance resources. Okay. Now let's check this the minimum number of resources of to escape the deadlock. What is the minimum number of resources required for escaping a deadlock situation? Minimum number of resources. Keep in mind, this is the minimum number of resources. You have to figure out the minimum number of. Let's say a system is currently four processes, and it needs 2 instances of resources. All of this process to complete these 4 processes. Let's say process P1, P2. Let's say process P1, P2, P3, and P4. You have total 4 processes, and to complete each process, you need 2 instances of resource R. 2 instances of resource R. 2 instances of resource R means that if this process, let's say just for an example, in sake of example, if this process P1 needs 2 printers, then if it is resources is printer, that means that to complete this process, process P1, it needs 2 printers, this process needs 2 printers, this needs 2 printers, this needs also 2 printers. So total 8 instances is required to complete these 4 processes. Now let's see that if you there is arbitrary, there is a process name called this R process. Resource R. There is so 2 instances of resource R is required to complete the each processes. So if you allow total R1, R2, total 8 resource from R3 till R8, if you have total 8 instance of R resource R, then this 4 processes completes the execution easily. Okay, each process will get this total 8 resources. So it's completes execution. Okay, but you have always resource limitation. We don't have any 4 or 8 computer, 8 let's say printers or kind of like this. So we have resource limitation. So here is condition is to execute the 4 processes, that the process that needs the 2 instances of resource from this R. So what is the minimum number of resources? This is the maximum 8, or you can go for more than 8. Then this 4 process can easily complete the execution because it needs 2 instances. So, but what is the minimum instance? You need to figure out this minimum instance for completing their execution. To compute this, you need to follow at first whatever their resources require. Whatever if this process require total n number of resources to complete this execution. Here is two resources is required. Here is if it is n instance resources required to complete the execution, n instance. So in that case, you need to assign to compute the minimum resource. You need to allocate n-1 resource for every process, to every process. Okay, here is 2 instances required. So n-1 is nothing but 1. So 1 is required. 1 is you need to assign 1 resource to every process. If it is 4 instances required to complete this execution, so you need to assign at first. You need to assign for n-1 is nothing but if it is 4, n is 4, n-4 minus 1 is 3. So 3 instance is need to assign for every process at first from this resource, and then you need to add extra resource, and that will be the actually minimum number. That will give you the minimum number. Here you need total 2 instance. So n-1 means that one instance you need to assign for every processes at first. This is let's say R1, R2, R3, and R4. You need to assign n-1 resource for every processes, and then you need to add extra resources. Let's say R5. Then you can avoid a deadlock. How? Let's say R4, P4 can can take these resources, extra resources, R5 and R4 and R5, and it completes the execution. Once it's completed execution, it will release these all resources. So here is R4 and R5. Then P3 can take these resources, and P2 can take these resources, and complete its execution, and it will release all of these resources. All of these resources. Then P1 can take one of these resources and complete its execution. Okay. From here, you can see that n-1 unit test for n-1, whatever that instance is required, then plus 1 will give you the minimum number of resources. Will give you the minimum number of resources for avoiding deadlock. But if it is 4 resources, let's say if it is only 4 resources, P2, P3, and then P4. If you have only 4 resources, R1, R2, R3, and this process already occupied all of these 4 resources, then there is a deadlock. Okay, it's to complete 2 instance. Then this process P1 will waiting for this another process. P1 waiting for here, and this P2 also waiting for here or here. Okay, this no process can complete its execution. Okay, so from here you can see how we can avoid this deadlock by using the minimum number of resources. All right. Do you have any questions or comment regarding today's topic? We talk about the counting semaphore as well as some part of binary semaphore, and then we talk about the deadlock and necessary condition of deadlocks. Talk about the resources, and there is 2 types of resources. One is the single instance resources, and another is multi-instance resources. And another important topic is how many what is the minimum number of resources to avoid deadlock. Okay, this is the summary of today's class. So any more questions or comments today? All right, if not, we can stop here today. I also saw your midterm exam. You did well. Okay, keep it up, and then okay, we can wait. We can stop here today and have a great evening. See you next class.